everyone. Welcome to the second half of the Machine Learning and Cloud Computing paper session. As always, please keep your phones on silent and wait until the end of the presentation for Q&A. We'll have a mic that we'll be passing around to people. Our first presenter will be Christopher Lau, who will be talking about the workload characterization of the shared/buy-in computing cluster at Boston University.
Good afternoon, everyone. Today I'll be presenting a project that I did over summer with Jonathan Klausner, Professor David Starobinski, Eran Simon, and Professor Azar Bastavros. We did this project on the shared computing cluster at Boston University. So here's an overview of my presentation. I'll first go over some background on computing clusters, and then I'll present the problem that we tackled in this project. And finally, I'll go over the methodology and briefly some results that we found. So the shared computing cluster is located in the MGH-PCC, the Massachusetts Green High Performance Computing Cluster in Holyoke, Massachusetts. This facility is shared with other universities like MIT, Harvard, UMass, et cetera. In our study, we only look at BU's shared computing cluster, so only BU's part of it. And this facility is actually pretty unique because it runs off of power generated by a nearby hydroelectric facility, so they get electricity at a reduced cost. Here's the SEC's architecture. So you could think of this as kind of a mini cloud. When the user logs into the SEC, he or she accesses one of the 4 login nodes via a secure shell. And these login nodes are just like a laboratory computer. You could do light computing tasks on them, like debugging or using a web browser. But if you want to do something more computationally intensive, like doing big data analyzing or a very lengthy MATLAB script, it would submit that as a batch job to one of the 467 compute nodes. And these batch jobs that run on these compute nodes are what we're analyzing. Here's some terminology that I'll be using. A job is, we define a job as a program or task run through the batch system. So we're not counting interactive programs, a program that requires user input. So a batch job is just you press enter and it runs. And the number of slots is also referred to as the number of CPUs or the number of cores that jobs use. So basically the number of computing units that a job requires. There's 3 types of resources on the SEC: shared, buy-in, and public. And I illustrate that in this diagram here. So as I've mentioned, the shared computing cluster at BU runs with a special unique architecture, a shared buy-in architecture. And on the left here, you see that users are divided into 2 groups. You have buy-in users and shared users. Buy-in users own their own group of resources, which we call buy-in resources. And there's also a large chunk of resources called the shared resources that's available to be used by any user, buy-in users or shared users. And the novel aspect of the system is that when buy-in resources are not being used by their owners, they're open to be used by any user, and we'll call these public resources, and it increases the utilization of these buy-in resources. So I'll go into a little bit more detail on these public resources. So first of all, they're not available when an owner submits a job. So what that means is if I'm a buy-in user and I submit a job to my own buy-in resource, then no other user can keep using that resource. So essentially, if an owner submits a job, then that's no longer a public resource. Any job submitted to public resources must not run over 12 hours. So this prevents buy-in owners from waiting for over 12 hours for their own resource. And lastly, public resources are beneficial to all users because it increases the pool of resources available to both buy-in and share users. So the Open Grid Scheduler is an open source software which the SEC employs. So it's a fair share scheduler. What this means is that every user has their fair target share. And when one user has a sharp increase in usage and uses the system more than their target share, they'll be penalized so the scheduler assigns them a lower priority so that other users get a chance to get their fair share. So essentially, the scheduler manipulates the priority of jobs in order to achieve an equal target share for all users. And also, as a side note, the priority of a job increases with the number of slots required. So larger parallel jobs will have a higher priority since they are harder to schedule just because of the sheer amount of resources they require. So here are the research questions that we tackle. So firstly, what are the performance benefits of public queues? So I mentioned that there definitely are benefits of these public queues since it increases the pool of resources available. But how do you quantify that? And what is the performance of the system in terms of utilization and users' waiting time? So utilization and waiting time, which I'll define later, are the two main parameters that we use to quantify the performance of the SEC. And how do the performance of shared and buy-in users differ? There obviously is an increase in performance experienced by buy-in users, or else no one will buy in. What are the factors affecting waiting time? And this is interesting because you want to see why do jobs wait longer and seeing what you can do to reduce that waiting time if possible. So this is the methodology. So the Open Grid Scheduler stores data on every single job in an accounting file, and we analyze around 10 gigabytes of that file. We use R and Python to process the data. So first, we partition the data, or cluster, if you will, into 3 different categories based on the resource that the job ran on: shared, buy-in, or public. And after partitioning that into these 3 groups, we further partition those jobs based on their request. And there are many different requests. As 2 examples, there's the number of slots requested or the runtime limit, and those are the 2 that we're most interested in. We ran statistics on running time, inter-arrival time, slots, and waiting time, and we'll focus on waiting time because that's the most interesting performance parameter that we looked at. So here's a timeline of the SEC. It went into production in June of 2013. It's continually expanding, and we only analyze data from January of 2015 to July of 2016. So we chop off the chunk of data where the SEC is still starting out, and there might be some anomalies. So what do we look for in these parameters? So the most interesting aspect is the distribution tail. And what that means is, for example, the percentage of jobs that wait longer than 12 hours, or the percentage of jobs that wait longer than 1 week, if you're talking about waiting time. And the reason that outliers are more interesting than the average job is because the user might not care if he's waiting an average of 2 hours, but it might be very important. It might be very important to notice that a few jobs wait longer than a week, and that might be troubling. So the standard deviation is one number that looks at this deviation of the outliers, and a median. We also look at the mean and the median. So I've been talking about waiting time and utilization a lot, and so how do we define this? The waiting time is a time between submission of a job and its execution. Other studies use the word delay, since saying that you're waiting might be a little misleading because you're not necessarily staring at a computer waiting for this program to finish. You could be doing other stuff. So the utilization we define as a ratio of slots used by a job as a ratio of slots used to the slots available, and that's a pretty standard definition for utilization. So now I'll go into a little more detail about the results that we found. Here's a utilization trend, the monthly average utilizations over the period that we analyzed. So lying on the bottom here, the pink line, that's the utilization achieved that would have been achieved by buy-in nodes if only their owners used them. The black line was the actual utilization of the buy-in nodes, so added in the utilization achieved by users who took advantage of the public resources. And on average, public resources reclaimed 17.4% of the capacity of buy-in resources. And considering how much computing power we're talking about here, that's a significant increase in efficiency. And that also takes some of the burden off of shared resources. So if public resources weren't there, then the jobs scheduled to public resources will be scheduled to shared resources, which already have a higher utilization. So there's three important factors that affect waiting time that we found. So there's parallel environment, which correlates with the number of slots, the total user usage, and the runtime limit of a job. I won't go over all our findings, but I'll give the results for the runtime limit as an example. So this chart shows the effect that the runtime limit has on the waiting time between shared and buy-in jobs. So the runtime limit is something that the user sets. So if you say your runtime limit is 12 hours, that means your job is not allowed to run over 12 hours. So for shared jobs, we see here that the standard deviation of the waiting time more than triples if you increase your runtime limit over 12 hours. And that's because, as I've mentioned in previous slides, you're not allowed to use the public resources if you have a runtime limit of over 12 hours. So we see that dramatic increase in waiting time. However, in the buy-in resources, the increase in waiting time, if you increase your runtime limit over 12 hours, is less, much less. So what we can conclude from this is that if you're a user that tends to run a lot of jobs for over 12 hours, that will be an incentive for you to buy in. So just briefly on the significance of our project. So as far as we know, our study is the first study to characterize a shared buy-in system. And the SEC at Boston University isn't the only computing cluster that implements this architecture. Other instances of shared buy-in architecture include the University of Wisconsin-Madison and the University of Arizona's HPC cluster. And HPC stands for High Performance Computing. So to conclude, the big question to ask here is, why buy? So why would you pay that fee to become a buy-in user? And from our study, so one reason would be that your waiting time is not satisfactory. You're waiting a very long time for your jobs. And there are three factors that can cause your waiting time to be high. If you're running a very large parallel job, for example, or if you have a high overall usage, in which case your priority on average will be lowered because you're using above your fair share, or if you tend to have jobs that run for a long time. So if you fall into any of those three categories, you will probably be considering to join the buy-in program because your waiting time is not satisfactory. And finally, moving forward, we could use the models generated from our study to simulate potentially more efficient policies. And some of these policies might be incentivizing users to use the SEC more during low periods of low utilization, so to take some of that burden off of peak utilization periods. And so simulation of these more efficient policies constitute the next step in this study. So finally, I would like to acknowledge the 4 NSF grants for supporting our research, and the Hariri Institute for Computing at BU. And I would especially like to thank the Research Computing Services Group at Boston University who've helped us tremendously over the summer. Thank you. So, any questions?
Hi. So when you are testing the scripts, are you taking into considerations of operating system schedulers such as BFS, CFS, like how they can potentially affect scheduling jobs simultaneously? So we didn't actually look into the scheduling aspect of the scheduler. So we tried to understand how the schedule worked, but that was not the focus of our study. So we mainly looked at the waiting time aspect of the shared computing cluster. So sorry, I don't have a very good answer to that question. Thanks. Any other questions? All right, thank you.
Good afternoon, ladies and gentlemen. My name is Khalid Saab, and today I'm going to be presenting my research on the estimation of cluster centroids in the presence of noisy observations. So just a quick outline. I'm going to motivate and formulate our problem, and then I'm going to give you my proposed optimal algorithm to solve this problem. Then I'm going to mention some common and intuitive algorithms in the literature used to solve this problem, and I'll compare my method with the common methods using a numerical example, and I'll end with some concluding remarks. So I want you to picture unlabeled data points, okay? They could be anything. They could be humans or robots, and you have two clusters. We have the green cluster over here, and we have the blue cluster. This graph over here represents their true locations. And we have their centroids over here, the diamond centroid and the triangular one. And so I want you to picture like a drone, and we have a measuring device on this drone. And it's taking snapshots of these clusters. And of course, like every other measuring device, there's going to be noise incorporated with the measurements. So maybe when the drone is flying very close to these points, the noise might look something like this. The X's are what we measure, and you can see this is just some small random errors, and they're a bit shifted from the true locations. But you can see that the centroids are measured pretty accurately. But sometimes when the drone is moving further away, we're going to have large noise. So the X's are deviated even more from the true locations, and the centroids as well. So we have all these two are replicates, so they're just snapshots. And we have all these replicates, we have M replicates, and with noise, and we want to see how we can estimate the centroids of each cluster. What should we do? Should we just use the replicate with the least amount of noise? Or should we use some combination between all the M replicates? So just some remarks. We're going to consider this noise to be additive white Gaussian noise, zero mean. These observations are taken collectively, so like the snapshots I was talking about. And as you can see, like between replicates, since the noise is going to be different, maybe this point over here, this X jumps to the blue cluster at one replicate and then the green cluster in another. So the number of points isn't constant between the replicates. And therefore, we can't really identify a point between the different replicates, so we cannot have any isolated processing on each point. So how does the data set look like? We have endpoints. Z is the true locations of the points. We have K clusters. And Cj is the true location of the jth, the centroid of the jth cluster. And our measurements, what we're observing, okay, have some error. So it's the true location plus some weighted error. V is nothing but the zero mean additive white Gaussian noise. And G is some deterministic function that weighs this error. So for example, in the drone, while it's moving further away, the errors are getting larger. It's due to this deterministic function G. So what we propose is that at each observation, we're going to apply k-means to get the measured centroid C hat. Sorry. Okay, sorry about that. And our proposed update algorithm, okay, our estimate centroid is C bar, and we're updating our estimate centroid by this term over here. In this term, we have our measured centroid C hat and some gain K. What this gain K is telling us is how much we should learn from the new measured centroid C hat. And so we want to find this gain K. Just some quick notations. The covariance matrix on the error covariance matrix on the noise is going to be denoted by R. Our weighted measurement error, which is the difference between our measured points and the true points, so Z minus Z hat, is going to be G transpose. And the covariance error on the measured centroids is like the average of the measurement error on the points. So GRG transpose over the number of points. This makes sense because we're using k-means, and k-means in k-means the centroid is nothing but the average of the points. So what I'm saying here is that the error on the centroid is the average of the error on the points. And so our estimate error covariance matrix is denoted by P, and this is going to be the difference between the true location of the centroid and our estimate location of the centroid, C bar. So we want to find this gain K such that this P, the mean square of the difference in our estimate centroid and the true location of the centroid is minimized at each replicate. It turns out that this is found recursively. Sorry. Bear with me, please. This is found recursively using these two formulas. So as we all know in recursion, we need some initial condition and terminating condition. The initial condition, P1, is just any positive definite matrix. It's just an initial guess. And the terminating condition is just that we have m replicates, a finite number of replicates. And so we use this initial guess of P1 and this first R1 equation. We get the gain K, and then from the gain K we get the next P, and so on and so forth. So the pseudocode of the algorithm, we have our observed points, Z hat. We're going to apply k-means. From that, we're going to get the measured centroid, C hat. From that, we're going to compute R, which is the error covariance matrix. We're going to obtain that optimal gain K, and using that gain K, we're going to update our estimate centroid, C hat. So some common methods out there and intuitive methods in the literature. First, method A is an intuitive one. All we do is use the replicate with the least amount of noise. And then method B is a more common one. It's we apply k-means on all the replicates and just take the average. And then in method C, we're going to stack the points over each other and apply k-means to that. So the numerical example is a simple toy example. We're going to have, again, just two clusters. The points are going to be generated randomly. And we're also going to consider two different deterministic functions for comparison, G1 and G2. So what k-means does is it tries to minimize this function s, which is the distances between the points and the centroids, and it sums it up between all the other clusters. And so S is using the true locations of the centroids, S hat is using our estimate locations of the centroids. And so we have to normalize this. So if S normal equals to 1, and this is in an ideal case where we have no errors, S normal equals to 1. And so we're going to consider three different scenarios. One scenario where we're going to fix the variance in the error. We're going to fix how many points we have, and we're going to vary how many replicates we get. In the second scenario, we're going to fix the variance in the error. We're going to fix the amount of replicates we have, and we're going to vary the number of points. And then in the third scenario, we're going to fix the replicates we have. We're going to fix the number of points, and we're going to vary how much variance we have in the noise. A Monte Carlo simulation was done where 1,000 independent runs were conducted for scenario 2 and 10,000 independent runs for scenarios 1 and 3. So for comparison, this is as for scenario 1, as the number of replicates is increasing, we see that our proposed algorithm defeats the other three common and intuitive algorithms. But something interesting about these results is that as m increases, our algorithm monotonically decreases, while this isn't the case for some other algorithms. And this is interesting because it's not really intuitive. You see, if you get a replicate with a lot of noise, you might think this is going to distort your results. However, what this is telling us is that no matter how much noise there is, the more replicates, the better. And then as we vary the number of points, we also see that our algorithm performs a bit better. But something interesting is that for the other methods, some of them cross over. See, sometimes B is better than A, and then sometimes A is better than B. And this is the same for methods A and C. So between the other three methods, there isn't one that's the best one. It's going to depend on the situation. It's going to depend on which deterministic function we're using, G1 or G2. It's going to depend on how many points we have. So this is another interesting result. As we vary the error, of course, the larger the error is, the worse the results. However, we see that the proposed algorithm is still giving better results. So just to conclude, we proposed this optimal algorithm that took advantage of the stochastics in the error, and we showed that it was superior over other common and intuitive methods in the literature. We also showed that the performance is going to monotonically improve as we get more replicates, and so it makes it robustly and effectively makes use of any noisy observations. Thank you.
Does anyone have any questions?
Yes, I was curious as to why you had 10,000 iterations for methods 1 and 3 and only 1,000 iterations.
Yeah, good question. This is just because as you increase the number of points, the computation gets much more extensive, and so it just took too long to wait for. But yeah, maybe we'll do this in the future. Thanks.
Any other questions?
Hi, I'm Pooja Hegde. I'm a high school student at Middlesex County Academy for Science, Mathematics, and Engineering Technologies in New Jersey. And my project focused on indoor positioning using computer vision. So why might this be important? We all know about GPS. It's pretty ubiquitous, and it's used basically by triangulation with multiple satellites and how long it takes for them to deliver messages to your GPS unit. And while this is used with tremendous success by many people for navigation and other purposes such as security, it is not very accurate in some cases, such as indoors, such as under high, tall skyscrapers. There can be very significant interference in these cases. So my question that I wanted to address is, how can I solve the problem of indoor positioning? So there are some methods that exist out there. Two major ones are Wi-Fi and Bluetooth, both communication-based. So the Wi-Fi method uses Wi-Fi access points, RSSI and MAC addresses, and analyzes that data from different Wi-Fi access points and tries to triangulate location. This has proven to be somewhat accurate, but it's not as accurate as other methods such as GPS, and it's also not very consistent. In addition, you need a lot of hardware to set this up, and it may not be reliable in many cases. An alternate method is Bluetooth low energy based solution, which has proven to be more accurate than the Wi-Fi solution, but it also requires setup and a lot of hardware, which may not be accessible to everyone. But why do we even bother with this? Why is this important? Well, indoor positioning, just like global positioning or outdoor positioning, can be used for applications such as navigation, for security, for tracking behavior. So the solution that we came up with was using something totally different, using computer vision and cameras to try to identify people in a room and try to locate where they are. And the tools we used varied. Mainly, the code was written in Python, but we also used the capabilities of OpenCV, which is an open source library for computer vision. We also used MATLAB for the data representation, the data filtering. And the hardware, the major component was Axis M1054 network cameras, which we actually used to synthesize the data. So our structure, our design structure consisted of multiple elements. First of all, we had the image processing step, where we took a raw image and we tried to make something of it, tried to identify and detect people. Then we had two components which we performed in parallel. One was calculating location, so where they are in a 3D environment, such as this room. And in addition, we also wanted to know who this person is. And to do so, we used a neural network to try to find out and match people based on from a 2D image into who they really are. After we did all this, we were able to synthesize this data and publish it to a server and the OWL model. So the first step, image processing. Now we have a video feed from the cameras, and we take a frame, and now we want to know, are there people in this image? Is there movement? And what we did was background subtraction. That was the first step, and after that, camera calibration. So the first step of the image processing was background subtraction, and as you can see on the slide, this was not a single step, but we had to perform multiple filtering steps in order to more adequately find a contour which captured the position. And to do so, our main algorithm was the background subtractor MOG2 provided by OpenCV, and after that, we used erosion and distortion techniques and dilation to help capture a better representation of the person. And with that cropped image, we were able to represent the person in the 2D setting, but not 3D yet. Another important factor that we had to consider was the distortion that the camera lens, the wide-angle camera lens, might provide, because the barrel and pincushion distortion could significantly alter because we care about location, right? So it could alter where the person is in actual real life. So we decided to account for this also using OpenCV and calculated camera matrices, distortion coefficients, and made sure that there's a low root mean square error, so that once we had pixel values, we could convert the pixel values that are in the raw image to the actual, perhaps more realistic pixel values, which actually represent what the actual field of plane looks like. One more thing. As you can see here, the OpenCV provides sample test cases, which they have pre-programmed parameters, such as this chessboard, and we used a set case test. We tested images and tried to calculate parameters using that. Now that we have identified contours of people inside an image. Now we want to know who they really are. And to do so, we used a neural network. And the first step that we did was detecting features. And this is by detecting average pixel changes and trying to identify features. And there's so many algorithms out there, such as SURF, BRISC, and SIFT. SURF was actually, it's non-proprietary for research purposes, so we decided to go with that. And as you can see from the image on the images on the right, top right, it can basically identify certain features and try to represent, use machine learning algorithms to represent that. And the second step was we used was k-means, which is discussed in the previous presentation. And we were debating whether to use k-nearest neighbor or k-means, but we decided that an unsupervised learning algorithm would be better because we don't know the size of the testing inputs and we don't know specifications about that because there could be a wide variety. And lastly, we trained a neural network that uses this data and matches the raw inputs into actual people that we have in a database. And if we wanted to add more users, right now for our testing purposes we had 2, but we could simply retrain the network in order to make it compatible with more users. So now the location calculation. How can you take a 3D world and represent it on a 2D plane and still be able to calculate where the person or where multiple people are? To do so, we had to utilize stereoscopic cameras, and we had to also utilize geometry. And first of all, we had Axis M1054 cameras, which are network cameras, and we set them up in such a way so that they were horizontally on the same level, same plane, and the separation was given. As you can see from the diagram, we have 2 cameras, right and left, and the cameras have a specific separation. There's also 2 angles labeled, alpha and beta. These angles are the angles made between the focal lenses of the camera and the angles which is made from the person to each camera. And we can calculate this by simply comparing the actual pixel length. So if it was 1080 by 720 image, it would be like 1080 pixels wide, and comparing it with how many actual pixels that the person is differing from horizontally from the center of the image to where they actually are. So using that, we can calculate the angles, the horizontal component of the angles. And with some geometry and trigonometry, we were able to calculate all the segments and all the lengths and actually triangulate the person inside the room. So here are some diagrams which depict some of our results that we have. On the top left, we have the red line represents the distance from the left camera to the person, the right camera to the person, and the blue line represents the distance from the left camera to the person. And as you can see, these 2 distances are slightly different. And this is what we utilize to actually calculate and give a sense of depth perception, because the 2 cameras are positioned slightly apart, and the differences in the pixels allow us to calculate angles and eventually calculate the actual position in a 3D environment. With some filtering, you can see on the right side that we have a plot on an XY coordinate plane of where a person moved over time, and it tracks to a good degree of accuracy where they actually are. Here's some other images. The left one is from the left camera in our setup, and the right one is from the right camera. On the top left, there's a label which tells you through the neural network who it is. This is not perfectly accurate, but it has a pretty high accuracy. In addition, there's a coordinate tuple at the bottom, and this represents your location, where 0,0 is which is the origin, is the bottom of the image at the very center horizontally. And both images are used to calculate the location. Here's a short video. As you can see, over time, the location of the person is calculated, and their name is calculated. Yeah, so there's some considerations which we haven't looked into fully. With more work we can, such as it kind of flickers sometimes because it's not perfect, but hopefully if we if we have a testing case or we have like a metric which tells you don't change it after this many recurrences, we can hopefully fix that. In addition, we encountered other issues such as the distortion was still very significant and the measurements became very crude as you left the screen or as part of your body was at the very corner of the screen. And this is because the further away you get from the center, the more the distortion is apparent, and the measurements seem to get more deviated from their actual value. And hopefully we can fix this by improving our camera calibration and trying to account for this in perhaps a different manner. In addition, we are thinking of increasing the accuracy with the inclusion of more than 2 cameras, so perhaps a better method for triangulation and comparison. Also, with more than 2 cameras, you could be able to get a better field of view of the entire area. We would also hopefully be able to better train the network so that we can identify the person better. And lastly, we wanted to make a more compatible solution, compact and compatible. So we were contrasting our benefits and the benefits with MATLAB versus Matplotlib, which is with Python. I would like to acknowledge those that helped me conduct this research, my partner Avi Cooper, who could not make it today, my parents, and also Rutgers University, which allowed me the research opportunity. In addition, Liberty Science Center provided me a grant as a high school student, and I could not have done the research without them. Thank you. Any questions?
A very fantastic project, yeah. I don't know if you have heard of Google's Project Tango. It's a very similar thing to what you've been doing, but other than moving objects or moving human beings, it's able to identify, say, furnitures, and then put them into course, or detect the position of them, but statically. So you think there's maybe in the future, is it possible by your algorithm to also identify positions and characteristics of non-moving objects?
Well, the algorithm we use right now for the position detection and identification relies on motion, actually. So we rely on the change in the pixel values. So perhaps if we had the location stands for itself, but the detection which we use right now is based on background subtraction, based on motion. So for non-moving objects, we would need a new algorithm to actually identify a contour and draw that bounding rectangle around what we're actually looking for. So if we were to come up with an alternate image processing algorithm, we could pair that with our existing identification and classification algorithms to hopefully create a solution to something that may be along the realms of what you're talking about. Any other questions?
I would highly recommend you to check it out, Google Tango.
All right, I will. Thank you.
Hi, my name's Connor. I'm going to be talking about some research I did this summer here at MIT on a problem called non-negative matrix factorization. And that is a lot of syllables, so we're going to abbreviate that to NMF. So what is NMF? It is a problem in which you're given a matrix, A, usually very large and very sparse, and you want to factor it into 2 matrices W and H. So you want 2 matrices W and H so that their product is A. However, we're going to impose the additional condition that these matrices be non-negative, which means that none of the entries in the matrix can be negative. Additionally, we're going to impose sizes on W and H. In particular, we usually want W and H to be very narrow, so that the reason we do this is because this forces all the data that's contained in A to be contained in fewer numbers because the W and H are smaller than A, and this compression sort of forces the whatever is solving the problem to find the underlying patterns in the algorithm, or in the data. And this can be very, very useful. In fact, there are lots of applications of non-negative matrix factorization. And just to go over a few of them, document clustering. So for example, if you have lots of texts and you want a computer to sort them by topic, you can use NMF, which is much easier than teaching a computer to learn English. Recommender systems. So if you go on YouTube and you're watching videos, and there's that sidebar that says, hey, here are some videos we recommend to you that we think you might like. That's NMF at work. NMF has applications in audio signal processing. It has applications in bioinformatics, where you can see which genes are most correlated. There's a wide variety of applications which involve NMF. And so I have some very good news, and that is that we have algorithms that solve non-negative matrix factorization very closely. I should note, because W and H are forced to be narrow, and because the entries in the matrix are non-negative, there isn't always an exact solution in W and H. We have algorithms that can pick W and H to be very close to being a factorization of A. So that's all well and good. Connor, what did you do your project on then? Because there's such a variety of applications, there's also a variety of algorithms that optimize for these different environments in which NMF is to be used. And there's new papers that come out pretty frequently, actually, that claim to solve NMF. And because of the nature of the problem, it's kind of difficult to tell whether an NMF algorithm is a good algorithm to be using or not. And there are several reasons for this. First of all, because there aren't actually exact solutions, it's hard to tell when an answer is good enough. We can use a cost function. In fact, usually the problem comes with a cost function, and you can say, this is exactly how far off our W and our H are from being a factorization of A. However, in fact, all NMF algorithms that we have so far only find a local minima of the cost functions instead of global minima. So that means that you get algorithms that means that the algorithms will give you good answers, but not the best answer, typically speaking. Also, looking at the nature of the applications, say if you take the document clustering, for example, it's not always perfectly clear what the correct answer to a solution is. If you have a document that's sort of in between topics, you may not know exactly how to categorize that, even as someone who's not a computer. The desired answer is not always well defined. Secondly, all the algorithms that we know of so far use randomness. So if you stick the same input into the algorithm, you can get vastly different answers at 2 different times, which can make it hard to tell how the algorithm behaves overall. Thirdly, the algorithms themselves are very complex in their behavior, so it can be you can't just look at them and say, oh, this makes sense that this works because logic. In fact, a lot of them, the only reason that we even know that these algorithms work is because we've tried it lots of times and they do. So it's very hard to tell whether an algorithm that is proposed by a paper is a good algorithm. Our solution to this problem is to try easy factorizations and plug them into the algorithm and see if they work. This is a very natural thing to do. In particular, we want to use matrices that have exact factorizations. So if we test a very simple matrix and we plug it into our algorithm, we should hope that it gives the exact factorization. because if our algorithm doesn't pass simple tests, there's no reason to think it would perform well on more complex data sets. So we plugged in the easiest matrix we could think of, which was the identity matrix. Obviously, there's a very trivial solution to this, which is the identity matrix times itself is the identity matrix. As it turns out, there are other solutions. We can choose other numbers to be on the diagonal. As long as the corresponding numbers multiply to 1, you're still going to get a product that is the identity matrix. Additionally, the rows and columns might be mixed up. As long as the rows of W are shuffled in a way such that they're in the same order as the columns of H, then you're still going to get a matrix that multiplies to the identity. And of course, you can mix those two. Those two variations to get solutions that look like that. And I apologize for the quality of that image. It looked better on my computer, I promise. But if you can see that, we have exactly one positive entry in each column and in each row. So that's a very easy thing to check. And in fact, we can prove that these are all the non-negative matrix factorizations of the identity. And we can generalize this to any diagonal matrix. If we change the values from being 1 to being anything else, then we still have solutions that look essentially the same. So this is a very easy thing to check. We can take our algorithm and plug a diagonal matrix in and see if the output is of the form that we see above. But that's not all we can do with these easy diagonal matrices. We can introduce perturbations into the matrix, what that means is to take some of the entries and change them by a very small amount. And intuitively speaking, if you have a matrix and you have a factorization, and then you change it just a tiny amount, the factorization should also just change by a tiny amount. However, as I mentioned before, there is randomness in the algorithms, so we have to make sure that we're using the same random seed as we did for the diagonal matrix when we perturb it and then run it again. So it turns out that if we do that, then our output will in fact be nearly the same as before. In particular, we looked at a perturbation that looked like this. And what this perturbation is we have numbers on the main diagonal that are of order 1, and then we have the diagonal above it, we have very small values above it of order epsilon, which we usually take to be around 10 to the negative third, 10 to the negative fourth, something like that. And as it turns out, W and H, there are exact solutions to A that look like that, and W and H look essentially the same as A, which is kind of cool. They also have order unity entries on the main diagonal, and then order epsilon entries on the diagonal above that. And again, this is easy to check. We know that the rows and columns may be shuffled, as I mentioned before, but they're fairly easy to unshuffle because the matrices here are triangular. So we can just look and see what the rightmost non-zero element is. Sorry, the leftmost non-zero element is in each row, and sort by that, and then we'll get our original. We'll hopefully get a matrix that looks like this if our algorithm works. Putting these two things together, this gives us a effective test to see whether a proposed NMF algorithm is a feasible algorithm. First, we run the algorithm on diagonal input, and we want to make sure that this that the output that we get is of the form that we saw before, where it has exactly one positive entry in each row and exactly one positive entry in each column of W and H. And that we can also multiply W and H together to make sure that they equal A exactly. Secondly, we can keep the same random seed as before so that we get, again, a solution that's going to look very similar. And we can run this again on the algorithm and see if we get the output that we saw before, that because we want our algorithm to spit out the exact solution, because there is an exact solution, and this is a fairly simple input. So if we do get our output in that form, where we have order unity entries on the diagonal and order epsilon entries above it, and then we multiply them together and we get something that's really, really close to A, then we know that our algorithm is in fact feasible. I will note that this algorithm does not necessarily, or that this test suite does not necessarily confirm that a algorithm does indeed solve NMF well, but it can at least weed out the ones that are very bad. So to conclude, I would like to thank the people that made my project possible. These are my advisors and Lincoln Laboratory, which funded the project. So thank you to them. I enjoyed working with all of them. So are there any questions?
On the matrices with the epsilon,
Yeah.
the 1 epsilon 0 matrix times 1 epsilon 0, does that give you 1 epsilon 0 or 1 2 epsilon 0?
Are you talking about this?
That one, yeah.
Okay, so I don't actually mean for those to be exactly equal to that. What I'm saying is that the matrices on the main diagonal are order 1, and the matrices on the diagonal above are order epsilon.
Okay.
If you multiply them out,
I think A comes out to 1 2 epsilon, 1 2 epsilon, at least if I do it.
yeah.
Okay.
Yeah, that should. Also, you'll note that there is an epsilon squared in the right corner, or the top right corner, which shouldn't happen. But it's okay because we're assuming the epsilon's really small, so epsilon squared is basically negligible.
Okay, thank you.
So, in practice, it turns out that usually one of the top row epsilons is 0 and one of the bottom row epsilons turns out to be 0. So actually only 2 of those supradiagonal entries are going to be positive.
All right. Hi, everybody. My name is Nick Anthony. I'm a junior at Brown. And I spent this last summer at the Scalable Computing Lab at Brown University studying limited precision deep neural networks. So to kind of get into this, to understand the research that I'm doing, you have to have...
otherwise we're videotaping it, so your voice won't.
So what we're looking into is understanding this research is understanding I'm going to begin with a ground-up level view of what neural networks are and kind of get into the nitty-gritty details of what I'm doing and how we're approaching these problems. So neural networks, they're the state-of-the-art solution to many machine learning applications. And so what is it? Kind of a form of trial and error learning. It deals with, it's trying to kind of this idea that image classification is a large problem. And so the best way to do this was actually to model it after the idea of a neuron, which takes a whole bunch of inputs here and combines them to prove an output activation. And so if we abstract this idea, we can kind of get the idea of a neural network. And so the important thing to notice is that you have input data, and in this case, it's RGB values, but it can be abstracted to even more things. And you take RGB values and you can weight them each of this input neuron. And for example, neural networks will usually in biological sense will give you an output of 1 or 0 in activation, but we will take that and just use it as more of an mapping to get multiple values and get more precision. So this is the idea. And so there's two things, important things that I'm going to point out here, which are going to be the basis of what we're trying to approach. First thing is that you'll notice that each one of these weights is kind of how networks learn. So when you approach this, is that we'll run through this whole thing of this training phase, where you train it and train it, where the network tries and fails, and we generate a loss function that allows us to update these parameters. And so by using this loss function, you can derive, and each parameter gets updated. And the second thing is that what I'm applying this to is going to be only the test phase, which is the deployment network, the network that you put out into the world. And so that requires no training. So what's the motivation? Well, current state of the art neural networks are doing very well, but what they are is that they are very deep and complex, which is great, which means that they've advanced, and the line innovation is they're having these fantastic accuracy returns. But as a computer engineer, we see the problem is, yes, that's fantastic, but that means that for every layer you add to these networks, it's more and more parameters. And so even for the networks, these simple networks that we're testing have 145,000 parameters to maintain. And so what you have here is not necessarily is beginning to be a power problem. And so what you have is that you're limiting these things now to these GPU-based systems, computer vision. You have an advanced architecture, but it can only be using these high computational units. So we're saying, what if you want to use them on devices with limited CPU power and memory? And so, for example, your smartphone is an example of the application. So we're saying, what if we want to use that? And so how can we do that? And the basic kind of key idea it comes down to is that it's mostly taken up in the memory subsystem. That to be able to maintain these parameters and compute with them is most of that power is being taken up and consumed by these parameters. So if we limit the precision of these parameters, that means less power, less memory. We have power efficient deep neural networks. So what we're looking for is the study for this, and a whole bunch of research has come out recently within this stage. And so we're saying, what if we got to take a step back and say, how exactly can we map these to the accuracies and values that we're using? So there's a lot of researchers come out saying, yeah, what if we use binary and fixed point and all this stuff like that? But there's no really reason why. Why are they choosing this one, like 16 bits? Why 16 bits? So the whole goal of this research is to really kind of map out this range of things implementations that you can use to get power efficient deep neural networks. So the focus of my research, I'm a subset of a larger research in this project, was the accuracy of these neural networks. So let's begin with, what are the solutions? So first things is using fixed point values as opposed to floating point. And what does this give us? Well, immediately nothing, but if you use dedicated hardware, it actually is easier to implement and actually will be more power efficient because there's just less logic required for each operation. So that's step one. And so this will also is a precursor to the next optimization that we use. It's going to be power of two weights. And so what does this mean? It means that every one of these weights is not in fact a number, but is a number of bit shifts that you can shift these input data. And so what does that mean? Well, you can now narrow down the number of bits you need for each weight because there's only so many multiplications by 2 or divisions by 2 until you zero out a value or max out a value, which is good. So now we're getting improved networks. And finally, binary weights, which is the whole network itself is just binary, which is a pretty idea. The only problem is that it's been explored and shows a lot of potential, but it shows decreased accuracy. So we'll explore that, talk about in a little bit about how to approach this problem. So how do you achieve the highest accuracy? That's our whole goal here. So the first thing is that we found that you want to train these networks with this limited precision. You don't just want to throw them in. So what's the issues here is more of a mathematical issue. So what it comes down with is that when you have this loss function, you're using stochastic, or you're using a form of gradient descent to achieve this ultimate minimum. And so the problem here is that you have these weight updates that happen are very, very small. They're very, very precise. And so when we're saying limited precision, there's an absolute resolution that you can update a value by. And so, for example, let's take a power 2 implementation. So if that's your weight and the update is 0.005, the weight's going to be negated back down to the 0.25 resolution, the 0.25 number. So what have we done? Nothing. And so to explore a little more into this, this means that these updates don't happen. You have a stagnant network that doesn't learn. So we have to figure out a better approach to this problem. And so in a more mathematical sense, you'll see that if these are our functions, what we have now is gone from a straight line to now a step function. And what's the derivative of step function? Is it 1 or 0? And so if it's 0, the network simply does not learn, which is an issue. So we want to take a step back and say, how do we approach that? So the solution is going to be based around this idea of this. The first implementation of the solution is this probabilistic or stochastic rounding that we do for each of these numbers. And so because we're dealing with low precision, it's something that actually has a large effect on a network. So one of the solutions that's been known to actually work is this idea of a stochastic rounding, which says that it'll round, but there's a chance it also might just round the other number, which means you can kind of preserve the gradient, in a sense, this derivative, just based on a randomness. The other things that we use is just a deterministic rounding scheme, and we ended up using a deterministic rounding scheme simply because it's easier to debug and use. And it actually shows stochastic actually does perform better, and we recognize this, and so future research is going to have to explore that. And so the second thing is we use a thing called the straight-through estimator, which is proposed in a previous work, which says that we're going to treat these updates not as a step function, but we're going to act like it is a complete function, and then the updates will happen after the round. So you kind of maintain this history, so you have a full smooth function here to generate these parameter updates. So how do we train these things? Well, we found that initialization is very key in this kind of networks. If you don't have a good initialization, it won't learn well. So the first thing is we said that, what if we train the networks with rounded weights from start to finish? Just round everything, let it go. And we found that, unfortunately, learning stagnates. It learns a little bit and then stops. So this won't work unless you have a better initialization method. So we said, well, what if we train the network full precision and then stick in the values and then round them and then continue training? Well, we found that it works well. It's not bad. But can we do better? Because we found that even though you can initialize that, again, we have the same problem where the learning kind of stagnates. So we said then, what if we just take a separate set of full precision parameters and create this kind of duplicate set of weights? And so you use initialization and maintain a full precision. And so all updates will go to this full precision. Then you round back into a limited precision to evaluate the network. And it turns out this actually works the best. So it's not a novel idea, but it turns out to be the best form of attaining a good limited precision neural network. So that's the idea. And so then we understand that then when you deploy this network, you're going to just take these low precision values and put them and deploy them onto whatever your dedicated hardware is or whatever your application is. So networks we use, just to give you guys an idea, we tested against MNIST. We use the Linnet architecture. You don't have to know what that is. Produce MNIST is just handwritten numbers and letters, and which is a relatively easier data set to work with. Then we went on to CPAR-10, which is a collection of 10 categories of images. They're 32 pixel by 32 pixel. That's why these are so low res, which is a much more tough thing to learn on. And we also adapted a custom net, which we said that if we had these limited precision values, could we increase the network size and create it deeper to account for these limited precisions? In which case, you're probably saying, well, didn't you just say that we want to decrease network size? And I would say yes, but if you're still achieving a more power efficient network, the higher accuracy cost is worth that little bit of extra computational power. So finally, we say yes. So it's still a better implementation. So results, what happened? We found that for accuracy, you can see here on the your guys' left, the floating point is the original network accuracy. This is for the MNIST numbers. We found that even at a fixed point 8.8 and a 4.4, we achieved about 92 to about 99% accuracy. So all performs very well. So there actually is almost no accuracy drop. The powers are 2 within 0.06, and we believe that just within a little more training, you'd be better. So good, it's a good start. However, how does it perform in CFAR 10? Well, we found that the floating point accuracy, they're too far left here, performs at 81.22%, which is good. And we rounded into these fixed point at fixed point 8, these 8/8. So these, just to explain, the number on the left is the bit width of the parameters, and on the right is the bit width of the data. So if you look into that and we get into powers of 2, performs within 4% accuracy. But we found that this is, if you take this number and approximate it out, you're having almost I'd say about a fourth of power consumption for only about a 4% accuracy drop. And we could say that that's well within reason. Now, what if you take this and expand to the custom architecture that we talked about before? Well, in fact, that you get the same accuracy results. So in essence, in this case, there really is no argument not to use all these networks because we have such a decreased power efficiency. We have a much more increased power efficiency for the same accuracy. And to take a step back and think about this, why does this work? Well, in a way, we found that this is it kind of makes sense in a way because this limited precision adds a sort of dropout feature to these networks, and as well, these networks are simply intolerant to this. Yeah, so where we go from here? Well, the idea is we're going to more explore this by binary networks, explore this idea of increasing network size, and finally, kind of generate the hardware metrics and really kind of map these values. And yeah, that's all I got. So I just want to say thank you to the Sohail, Professor Bahar, and Professor Rada, they're my lab, helped me do this workshop, helped me do all this research, and they're very helpful, and they're continuing this research as we talk right now. So thanks. Any questions? You do save that's the whole point. We're still in the process of checking these exact time measures. You don't actually save a ton of in terms of each pass in terms of time. You don't actually save that much time because a forward pass is when you actually play network, you don't gain a ton in terms of time. It's more about the power and memory that we're exploring here. And so these networks we're proposing consume the numbers you have around a fourth of the power or even less. Those exact metrics, I think, they're in a different stage right now.
I enjoyed your talk, by the way, but you said that you were doing it only on CPUs. I was curious if there was any plans to test the same benefits on GPUs as well. Because, yes, you do have the extra power, but the way you're going at it, just by saving the power so you can keep it on the CPU, that would actually be quite helpful when you look at all the research going on.
So you're saying if we can do
the work you were doing, that was done on only CPUs, right?
So you can test it for both on GPUs and CPUs.
Right. You were just looking on the benefits for CPUs, so
Exactly.
Right.
Yeah.
Do you plan to test that as well, see if there's any correlate difference on GPUs as well, or because the architecture is a bit different computationally?
Yes. So that's the thing. So you have to understand. I agree. And so it's an interesting thing where a fixed point on a GPU doesn't make much sense because they've been generated, they've been made to be optimized for a floating point. So that's one thing where it's not necessarily we would like to test our metrics against a GPU, but ultimately the whole system is going to be to kind of couple this with a custom dedicated hardware computational unit that will do this very efficiently. And so in that respect, that's the reason why we started talking about fixed point and this kind of bit shifting, because that's something you can implement directly in the hardware, and therefore it'll run extremely power efficiently in that dedicated hardware.
Like an ASIC, you mean?
FPGA, and eventually
Yeah.
ASIC, yeah.
Gotcha.
It depends on if you wanted to get started printing a lot of these, you're using ASIC, yeah.
So I'm not not too familiar with machine learning, but I saw that you were using MNest and ImageNet, so you guys were using supervised learning on this stuff?
Yes.
Have you tried it on unsupervised learning? Because it's possible that you could generate a label vector that is better fit to the bit shifting.
I don't have a great answer other than for this machine learning for these deep neural networks, it's very complicated to get these things to work well, and it is in itself a whole industry of research that goes into these, and so the whole core of this research is how to implement these networks in a power efficient way, not as much into the actual in-depth and mathematical reasons why and why they don't work. I guess is my response.
Any other questions?
Thank you.